Hello and welcome to the stream. This is day 4 of learning OpenGL, and today we are going to be learning about textures. We learned that to add more detail to our objects, we can use colors for each vertex to create some interesting images. However, to get a fair bit of realism, we'd have to have many vertices, so we could specify a lot of colors. This takes up a considerable amount of extra overhead, since each model needs a lot more vertices, and for each vertex a color attribute as well. What artists and programmers generally prefer is to use a texture. A texture is a 2D image. Even 1D and 3D textures exist, used to add detail to an object. Think of texture like a piece of paper. Okay, we can just skip this. Below you'll see a texture image of a brick wall mapped to a triangle with the previous chapter. In order to map a texture to the triangle, we need to tell each vertex of the triangle which part of the texture it corresponds to. Each vertex should thus have a texture coordinate associated with them that specifies what part of the texture image to sample from. Fragment interpolation then does the rest for the other fragments. Texture coordinates range from 0 to 1 in the x and y axis. Remember that we use 2D texture images. Retrieving the texture color using texture coordinates is called sampling. Texture coordinates start at 0, 0 for the lower left corner of a texture image to 1, 1 for the upper right corner of a texture image. The following image shows how we map texture coordinates to the triangle. We specified 3 texture coordinate points for the triangle. We want the bottom left side of the triangle to correspond with the bottom left side of the texture, so we use 0, 0 texture coordinate for the triangle's bottom left vertex. The same applies to the bottom right side with a 1, 0 texture coordinate, and the top of the triangle should correspond with the top center of the texture image, so we take 0.5 and 1 as its texture coordinate. We only have to pass 3 texture coordinates to the vertex shader, which then passes those to the fragment shader that neatly interpolates all the texture coordinates for each fragment. The resulting texture coordinates would then look like this. Okay, so we have an array texture coordinates, and these are the texture coordinates for each of the 3 vertices of this triangle. Okay. The texture sampling has a loose interpolation and can be done in many different ways. It is thus our job to tell OpenGL how it should sample its textures. Texture wrapping. Texture coordinate usually ranges from 0, 0 to 1, 1, but what happens if we specify coordinates outside this range? The default behavior of OpenGL is to repeat the texture image. We basically ignore the integer part of the floating point texture coordinate. But there are more options OpenGL offers. So we can set the texture wrapping to GL repeat, GL mirror repeat, clamp to edge, and clamp to border. Okay, so that gives us these results. Each of the aforementioned options can be set per coordinate axis S, T, and R if you are using 3D textures equivalent to X, Y, and Z with the GL text parameter function. So here's an example of that. GL text parameter I, giving the GL texture 2D, GL texture wrap S. Okay, you have to set it separately for each of the axes. The first argument specifies the texture target. We're working with 2D textures, so the texture target is GL texture 2D. The second argument requires us to tell what option we want to set and for which texture axis we want to configure it for both the S and T axis. The last argument requires us to pass in the texture wrapping mode we like, and in this case OpenGL will set a texture wrapping mode on the currently active texture with GL mirrored repeat. Alright, if we choose the GL clamp to border option, we should also specify a border color. This is done using the FV equivalent of GL text parameter function with GL texture border color as its option when we pass in a floating array of the border's color value. So GL text parameter has different variants. It has GL text parameter I and GL text parameter FV. Okay, and this is used to set the texture border color. Texture filtering Texture coordinates do not depend on resolution but can be any floating point value. Thus, OpenGL has to figure out which texture pixel, also known as a texel, to map the texture coordinate to. This becomes especially important if you have a very large object and a low resolution texture. You probably guessed by now that OpenGL has options for this texture filtering as well. There are several options available, but for now we'll discuss the most important ones: GL nearest and GL linear. Okay, so this is the GL nearest texture filtering. This is the default method. GL selects the texel that the center is closest to the texture coordinates, so it samples the 4 around it, and whichever one is the closest one, that's the one that it actually samples. For GL linear, also known as bilinear filtering, takes an interpolated value from the texture coordinates. Neighboring texels approximate a color between the texels. The smaller the distance from the texture coordinate to the texel's center, the more the texel's color contributes to the sampled color. Okay, so it sort of takes a weighted average of the 4 pixels around it. But what is the visual effect of such texture filtering method? Let's see these methods work when using a texture with low resolution on a large object. So this is GL nearest. It sort of has this pixelated look to it, and GL linear kind of blurs the image, but it gets rid of these sharp edges. GL nearest results in block pattern. Yeah, that's what we said. Texture filtering can be set for magnifying and minifying operations when scaling up or downwards. So you could, for example, use nearest neighbor filtering when textures are scaled downwards, and linear filtering for upscaled images. We thus have to specify the filtering method for both options via GL text parameter something. This code should look similar to setting the wrapping method. So you got the same GL text parameter I, but this time we need to specify that we want to set the GL text min filter or the mag filter, and here we want to set it to GL nearest and the mag filter to GL linear. Finally, we have mip maps. Imagine we had a large room with thousands of objects, each with an attached texture. There will be objects far away that have the same resolution. I guess I can skip this part. Okay, so we have mip maps. When an object is far away, it uses a smaller resolution of their texture. Creating a collection of mip map texture for each texture image is cumbersome to do manually, but OpenGL does it automatically. We use the function GL generate mip map. When switching between mip map levels during rendering, OpenGL may show some artifacts like sharp edges visible between the 2 mip map layers. Just like normal texture filtering, it is also possible to filter between mip map levels using nearest and linear filtering for switching between mip map levels. To specify the filtering method between mip map levels, we can replace the original filtering method with one of the following 4 options. Okay, so even when you are switching between mip maps, you can set a filtering method for that. GL nearest, mip map nearest, GL linear, mip map nearest, GL nearest, mip map linear, and GL linear, mip map linear. Okay, so you're setting the interpolation mode and the mip map interpolation at the same time. So you use the same function GL text parameter I, and then you want to set GL linear mip map linear. That will also set the interpolation for the mip map as well. A common mistake is to set one of the mip map filtering options as the magnification filter. Okay, so for mag filter, this doesn't have any effect since mip maps are primarily used for when textures get downscaled. Texture magnification doesn't use mip maps, and giving it a mip map filter option will generate an OpenGL GL invalid enum error code. Okay, so we have to make sure that we don't pass a mip map option for the mag filter. Loading and creating textures. The first thing we need to do to actually use textures is to load them into our application. Texture images can be stored in dozens of file formats, each with their own structure and ordering of data. So how do we get those images in our application? One solution would be to choose a file format. We'd like to use, say, PNG, and write our own image loader to convert the image format into a large array of bytes. While it's not very hard to write our own image loader, it's still cumbersome. And what if you want to support more file formats? You then have to write an image loader for each format you want to support. Another solution, and probably a good one, is to use an image loading library that supports several popular formats and does all the hard work for you. A library like stbimage. Okay, I guess we're gonna need to include this stbimage.h. stbimage.h is a very popular single header image loading library by Sean Barrett that is able to load most popular file formats and is easy to integrate in your projects. stbimage can be downloaded from here. Simply download the single header file, add it to your project as stbimage.h, and create an additional C++ file with the following code: hash define stbimage implementation, and then we include stbimage.h. By defining this stbimage implementation, the preprocessor modifies this header file such that it only contains the relevant definition source code, effectively turning the header file into a CPP file. And that's about it. Now simply include stbimage.h somewhere in your program and compile. For the following texture section, we're going to use an image of the wooden container to load an image using stbimage.h. We use stbi load function. All right, let's first get stbimage. All right, and then it says to create another file, create an additional C++ file with the following code. Okay, we should put this header file inside here. Nope. Okay, it's not showing the header file here for some reason. Guess I'll just copy it manually. And then edit it. Okay. Okay, yeah, now there's no error. Now I can include it here. And it should run without any errors. All right. So we did this. We set the width and the height and the NR channels. Unsigned char pointer data is equal to stbi load, and then we give it the image path, width and the height, and the NR channels. The function first takes as input the location of an image file. It then expects you to give 3 ints as its second, third, and fourth argument. that stp image.h will fill with the resulting image's width, height, and number of color channels. Oh, it's the number of color channels. We need the image's width and height for generating textures later on. Like any of the previous objects in OpenGL, textures are referenced with an ID. Let's create one. GLGen textures. The function first takes as input how many textures we want to generate, stores them in an unsigned int array, given as its second argument, in our case just a single unsigned int. Just like other objects, we need to bind it, so any subsequent texture commands will configure the currently bound texture. So then we do glbind texture. Now that the texture is bound, we can start generating a texture using the previously loaded image data. Textures are generated with GL text image 2D, and then GL generate mipmap to generate the mipmaps for that. Once GL texture image 2D is called, the currently bound texture object now has the texture image attached to it. However, currently it only has the base level of the texture image loaded, and if we want to use mipmaps, we have to specify all the different images manually by continually incrementing the second argument, or we could call GL generate mipmap after generating the texture. This will automatically generate all the required mipmaps for the currently bound texture. After we are done generating the texture and its corresponding mipmaps, it is good practice to free the image from the memory. stbi image free data. Okay, the whole process of generating a texture thus looks like this. Alright, so let's do that first. Before rendering anything, or should I do this at the top? Okay, let's just do this here. Texture. Okay, so first we are doing a glgen textures and GL binding that texture to GL texture 2D, and then we are going to set the texture wrapping filtering options on the currently bound texture object, which will be this, and then after that we are actually going to load and generate the texture right here using the STBI library. And then finally we'll just free the data. Okay, hopefully if this doesn't generate any errors. Okay, it's saying, oh, I forgot to add the image, this one right here. Okay, now it should work. Yep, this time we didn't get any errors. For the upcoming section, we'll use the rectangle shape drawn with GL draw elements from the final part of the Hello Triangle chapter. We need to inform OpenGL how to sample the texture, so we'll have to update the vertex data with the texture coordinate. Okay, I'm actually going to take a break. Okay, we're back. We have already loaded the image. Now we need to apply the texture. For the upcoming section, we'll use the rectangle shape drawn with GL draw elements from the final part of Hello Triangle chapter. We need to inform OpenGL how to sample the texture, so we'll have to update the vertex data with the texture coordinates. Okay, actually I don't have the rectangle on the screen, I have the triangle. Yep, so I guess we'll have to make some edits. So we're gonna need to change the vertex data. We have the position, color, and the texture coordinates. So here we need to add the texture coordinates to this. Okay, this is the old one. Let's add this. This is the rectangle. I don't think it's gonna work. Yeah, it doesn't work. Okay, since we've added an extra vertex attribute, we again have to notify OpenGL of the next vertex format. Okay, yeah, because now we have added these two texture coordinates. This gets added to this, so the stride is actually going to increase. And is the offset okay? For the RGB, the offset is going to be the same, but for the texture we're going to need define the offset as 24 because we want to skip these 6 floats and read it from here. Okay, so let's see, can I do this on my own? Okay, I think this is the one. I don't think the position is going to change because it's the first 3. It's not going to change either. Well, the stride is going to change, right? First the stride was only 6. I think now it's going to be 8 for both of these. This is the starting point, I think, right? It's the offset. Offset is not going to change. We actually need to add another vertex attribute here for the texture coordinate. Okay, so it's gonna be at position 2. I think, what is 3? Is 3 like the number of values? In that case it will be 2. This is the same. Okay, this I think is the stride, which will be, is it the stride? Yeah, it will be the same for all of these, so it's 8. And then the offset is gonna be 24. So this starts from 0. This skips the first 3. This need to skip the first 6, I believe. Let's actually cross check. Okay, 2, 2, 8 times the size of float, and then 6 here. Yep. Okay. Note that we have to adjust the stride parameter of the previous 2 vertex attributes to 8 as well. Next, we need to alter the vertex shader to accept the texture coordinate as a vertex attribute and then forward the coordinates to the fragment shader. Okay, so here it is actually going to be another layout like that. Let's actually open the vertex shader. We already have layout 1 and layout 0 and 1. We need to add layout location 2. This will be an in vector. I think it's a vector 2, right? Yeah, it's a vector 2. And we can call it a text coord. Okay. And then we'll just pass this as an out, so it reaches the fragment shader. We already have the color out. We'll just add out, yep, vec 2. What is it called? Text coord. Okay. Here, and then we're just gonna assign this. Okay. Okay, this should be text, not text. And I think that's it. Now for the fragment, it should accept the text coord. Yeah, it needs to have the same name and data type. So here it's going to be an in the fragment shader. Okay, and then we're gonna have a uniform for our texture. Okay, it's gonna be of type sampler 2D. Our texture. And then we can set the frag color. Okay, it has a texture function, it seems, to apply texture, and you pass the texture and the texture coordinates. Okay, where was I? The fragment shader should then accept the text coordinate output variable as an input variable. The fragment shader should also have access to the texture object. I don't think we passed the object yet, but how do we pass the texture object to the fragment shader? GLSL has a built-in data type for texture objects called a sampler that takes as a postfix the texture type we want. For example, sampler 1D, 3D, or in our case 2D. We can then add a texture to the fragment shader by simply declaring a uniform sampler 2D that we later assign our texture to. Okay, to sample the color of a texture, we use GLSL's built-in texture function that takes as its first argument the texture sampler and as its second argument their corresponding texture coordinates. The texture function then samples the corresponding color value using the texture parameter we set earlier. The output of this fragment shader is then the filtered color of the texture at the interpolated texture coordinate. Okay, this makes sense. So this is a texture, this is a sampler 2D type. That's why we pass in a vector 2. So I'm guessing if this was, say, a sampler 3D, this would be a vector 3. And if this was a sampler 1D, this would be a float, but that's just my guess. All that's left to do now is to bind the texture before calling GL draw elements, and it will then automatically assign the texture to the fragment shader sampler. Okay, yeah, we have to pass in the texture data. So we do GL bind texture. GL bind texture, and we say GL texture 2D and texture. Did we already do this? GL bind texture, GL texture 2D, and the texture. It seems like we already done this before. I'll just keep it in comments for now. GL bind vertex array. Oh, okay, is this doing inside the render loop? I think it is. GL bind vertex array, which we are doing here. GL bind vertex array, and then GL draw elements, GL triangles, GL draw element, GL triangles 6, GL assigned int 0. Okay, I guess we'll just do this here. That's not it. Oh yeah, we need to set our indices as well. First we need to draw the left upright triangle. So top right, bottom right, and bottom left. Then we need to draw top left, bottom left, bottom left, and top right. So 1, 3, 4. Nope. Number of indices is 6. It seems like it's still reading 3 somewhere. Where do we set that? Well, I am telling it to draw 6, aren't I? The second parameter is specify the number of vertices / elements to draw using indices. GL bind vertex array. Do this. Okay, this is just unbinding it. Is this correct? 0, 1, 2, 3. 0, 1, 2, 3. Okay, this can't be 4. We need bottom right. No, we don't need bottom right. Let's set it 0, 2, and 3. So that will be skipping the 1. Top right, bottom left, and top left. Okay, yeah, that makes sense. Okay, we have our texture. If your rectangle is completely white or black, you probably made an error. To get a little funky, we can also mix the resulting texture color with the vertex colors. We simply multiply the resulting texture color with the vertex color in the fragment shader to mix both colors. Okay, so this is our texture, and we can take our color and multiply it with this. So we are getting our color here, but we need to convert it to vec 4 first. Okay, let's try that. Okay. I guess you could say our container likes to disco texture units. You probably wondered why the sampler 2D variable is a uniform if we didn't even assign it some value with GL uniform using GL uniform 1i. We can actually assign a location value to the texture sampler, so we can set the multiple textures at once in a fragment shader. This location of a texture is more commonly known as a texture unit. The default texture unit for a texture is 0, which is the default active texture unit, so we didn't need to assign a location in the previous section. Note that not all graphics drivers assign a default texture unit, so the previous section may not have rendered for you. The main purpose of texture units is to allow us to use more than one texture in our shaders. By assigning texture units to the samplers, We can bind to multiple textures at once as long as we activate the corresponding texture unit first. Just like GL bind texture, we can activate texture units using GL active texture, passing in the texture unit we'd like to use. GL active texture, GL texture 0. Activate the texture unit first before binding texture, and then GL bind texture. After activating a texture unit, a subsequent GL bind texture call will bind that texture to the currently active texture unit. Texture unit GL texture 0 is always by default activated, so we didn't have to activate any texture unit in the previous example when using GL bind texture. OpenGL should have at least a minimum of 16 texture units for you to use, which you can activate using GL texture 0 to GL texture 15. They are defined in order, so we could also get GL texture 8 via a GL texture 0 plus 8, for example, which is useful when we'd have to loop over several texture units. We still, however, need to edit the fragment shader to accept another sampler. They should be relatively straightforward now. Okay, yeah, so here, where's our texture? It will be in fragment shader. We can just make another uniform sampler 2D, texture 1, texture 2. Still works, right? Yep. Okay. And then what is it doing? It's actually mixing between texture 1 and texture 2, and then I think this is a mix factor. The final output color is now the combination of two texture lookups. GLSL's built-in mix function takes two values as input and linearly interpolates between them based on its third argument. If the value is 0, it returns the first, blah blah blah. We now want to load and create another texture. You should be familiar with the steps now. Make sure to create another texture object, load the image, and generate the final texture using GL text image 2D. For the second texture, we'll use an image of your facial expression when learning OpenGL. Save image as. Okay, yeah, it's the same as before. This is texture 1. Let's do texture 2. This will be our data. We're loading this image. We get the width and the height, and then we're doing GL text image 2D and then generating the myth map. Note that we now load a .png image that includes an alpha transparency channel. This means now we need to specify that the image data contains an alpha channel as well by using GL-RGBA. Otherwise, OpenGL will incorrectly interpret the image data. To use the second texture and the first texture, we'd have to change the rendering procedure a bit by binding both textures to the corresponding texture unit. Okay, so we need to bind both of them. Here we're doing bind texture D1. We need to create texture 1 and texture 2. texture wrapping, I think this also needs to be done again. Okay, don't see any errors. I guess the second texture is loaded as well. Now we need to use it. We also have to tell OpenGL to which texture unit each shader sampler belongs to. Wait, let's actually try to mix it here. Okay, the second one is loaded. We're doing active texture, GL bind texture 1, and then active texture 1, and then binding texture 2 to it. How will it know which one it is? I'm doing active and bind here. I'm doing gen texture for this. GL gen texture and then GL bind texture here, same as here. Do I need to activate it before that? I guess we'll see. What is this? Our shader.use. Don't forget to activate the shader before setting uniforms. GL uniform 1i. Our shader ID and and then texture 1 0. Set it manually. Set int texture 2 1 or with shader class. Okay, let's try this. We have to call this before. Nope. By setting the samplers via GL uniform 1I, we make sure each uniform sampler corresponds to the proper texture unit. You should get the following result. Okay, I don't think I copied the image. Okay. You probably noticed that the texture is flipped upside down. This happens because OpenGL expects 0, 0 coordinates on the y-axis to be on the bottom side of the image, but images usually have 0, 0 at the top of the y-axis. Luckily for us, STV image can flip y-axis during image loading by adding the following statement before loading any image. Okay, so wait, this was the first texture was also flipped, I guess. So we do that here. Yep. If you see one happy container, you did things right. You can compare it with the source code. Firstly, the only reason I learned how to do this. Okay, do we have any exercises? Make sure only the happy face looks in the other reverse direction by changing the fragment shader. Make sure only the happy face looks in the other direction. Okay, so I need to flip it somehow. What if I give it a negative texture coordinate? Okay, no, it also goes upside down. Let's do -2. -y. Okay, I think it should be -x. Okay, yep, that flips it on the x-axis. Experiment with the different texture wrapping method by specifying texture coordinates in the range of 0 to 2 instead of 0 and 1, and see if you can display 4 smiley faces on a single container image clamped at its edge. Okay, we want to show 4. Okay, let's first get rid of this. Just double everything. Yep, okay, it shows 4. See if you can experiment with other wrapping methods. Okay, was there some sort of a warning? So for the rapid methods, GL repeat, what's it mirrored? GL mirror repeat. Okay, yeah, it's mirroring on the x-axis. They should mirror on both. Yep, so this is upside down. Okay, so this is the first one, and then it mirrors on these two axes. Okay. And we have clamp to edge and clamp to border. Okay. Maybe I need to set a border color for this. Yep. Yeah, I'll just set it to repeat for now. Okay, what else? Try to display try to display only the center pixels of the texture image on the rectangle in such a way that the individual pixels are getting visible by changing the texture coordinates. Try to set the texture filtering method to nearest. See the pixels move clearly. Try to display only the center pixels of the texture image on the rectangle in such a way that the individual pixels are getting visible by changing the texture coordinates. What? In such a way that the individual pixels are getting visible by changing the texture coordinates. I don't think I understand that. Use a uniform variable as the mix function's third parameter to vary the amount of two textures are visible. Use up and down arrows to change how much the container or the smiley face is visible. Use a uniform variable as the mix function. Okay. Uniform float like that. Okay, I need to see how to set the uniforms. GL uniform 4F, and then it's after the use program for GL uniform 4F. So it will be here. Our shader dot set float in this case. Wait, maybe I should set it at position 3. Okay, maybe I'll just create a variable for that. Is it like this? Okay, seems to be working. Or is it? So it needs to be between 0 and 1. That's what I'm doing here. No, I don't think it's getting passed. Takes the ID and name.cstring away. So yeah, that's what I'm passing. I'm passing it the ID and the name. It already knows the ID, so I don't think you need to pass the ID. Yep, you only need to pass the name and the value. Oh, this is the value. Okay. I think it needs to be like this. Text mix vector, yeah. Text mix vector. Okay, I think it's working now. Yep. So I need to do something with this. Process input. Okay, I haven't clamped it yet, but let's see if this works or not. Nope. Okay, let's first try to print it. Okay. Do I need to bind it every time? Yep. Yeah, I should probably clamp it. Does that put clamp function? I think it does. Oh, it's std clamp. Std min. Alright, so now the values clamped between 0 and 1. Okay, I think we're done with the exercise. Okay, I still don't understand what this is. Okay, so it has changed the texture coordinates. Note that we changed them to zoom in on our texture image. Okay. Set the container wrapping method to GL clamp to edge. Set the filtering to nearest. I don't think I understand it. Try to display only the center pixels of the texture. I think it just means that just decrease the size of this. Rather than being from 0 to 1, set it to like 0.5. Set this to nearest. Yeah, okay. I think we're done with the chapter. Next one is going to be transformations, which I guess we'll do next week. That's it for the today's stream. If you want to watch the previous videos, I actually upload everything to YouTube, so just go to the about section and you'll find the YouTube link. So you'll find all of the previous videos here. You can actually follow along if you want. And yep,